recall that the limit as x approaches a of f of x equals L, even though f of a may not exist. The same idea actually holds true in 3 space. What this is saying in R2, well, let's take a quick example here. Suppose I say f of x equals, and I use kind of an overused example, but it gets the point through, x squared minus 4 over, say, x minus 2. And what I'm interested in is I want to know what the limit is as x approaches 2 of f of x. Well, clearly at 2 I have 0, right? Well, as x approaches 2, what I actually end up with is 0 over 0. So I can think of this as actually being equal to x minus 2 times x plus 2 over x minus 2. Clearly the x minus 2's cancel, and I end up with simply x plus 2. So if I graph this thing, I know the graph of this function is going to look like this. Let's see, 1, 2. But I'm going to have a hole when x actually equals 2. And that hole is going to be at y equals 4. And the reason I know that, because here, this modified version of this equivalent equation or equivalent function can be evaluated at x equals 2. If I evaluate this at x equals 2, I get 4. That's supposed to be a 2. There we go. So I know the value right here, it actually has the value of 4. But because of an original function, I end up with this 0 over 0 situation. Then I know what I have is a hole here. So the function itself is undefined when x equals 2, but the limit, because as I approach from the left and the right, as I approach 2 from left and the right, the function approaches the same limiting value, that being L, which is 4. Now, again, in 2 space, oops, let me fix that. That's not what I wanted. There we go. Again, in 2 space, as I approach, say, A, if my function looks like this, as an example, here I have a situation where clearly the limit does not exist, because as I approach A from the left, I am approaching this value of L, say L1, and as I approach A from the right, then I'm ending up approaching this value of L, say L2, and here L1 is not equal to L1 is not equal to L2, therefore the limit doesn't exist. Now, I realize that I really didn't tell you anything that you didn't already know. This is basic stuff from way back in Calculus 1. But the point here is that the exact same idea holds true for 3 space. Now, in 2 space, if I approach A from 2 directions, right, which I need to check it, and one of those directions comes to a different L, a different limiting value, then the limit doesn't exist. And it's the exact same idea in 3 space. So if I can find 2 different paths, now remember there's an infinite number of possibilities, but if I can find 2 paths of approach to A for which the limits are different, then again the limit doesn't exist, just like here. The only difference is in 2 space is there's only 2 paths I can take. So the trick here is really when working in functions of 2 variables, how do I check those paths? There's an infinite number of them. And the answer is really you don't check all of them. What you end up doing is rather than trying to find out where the thing is defined, so to speak, we just look for where it's not defined. We look for problems, not where it behaves nicely. And then there's some logical approaches that we can take to help us out with that.